maximum. By now you must have understood what is the meaning. A posteriori, that is what is map estimation. So I'll write it in bracket here itself, map. A posteriori means after we have got the posterior. Okay, so what is map? What does it do basically? What is the theory behind this? So maximum a posteriori estimation, what does it do? It finds the peak of the, say for example, we assume that this is a Gaussian. So there is a Gaussian. Okay, so this will find the, in Gaussian the mu is also the peak or whatever. Okay, so this peak value, so if it is Gaussian or perfectly symmetrical, right, the peak coincides with the mean. Okay, but then all the distributions it may not be the same. So whatever is the peak value, say for example, even if it's skewed like this, right, so the peak may not be the mean. Okay, the mean will be somewhat on this side and it may not be the mean. Okay, so that's the case. So the whatever is the peak value, so the peak value tells me the mode of this distribution, because most of this this is a PDF, right? This is a PDF. So the peak here, this peak will tell me that what is the value around which the probability of finding something is maximum. This is a probability distribution. So at this value, whatever is the peak, so we'll have the maximum number of entries. That's why the probability is high here. So this is your mode or the peak. The peak means mode. Mode means which entry has the highest count. Say for example, what is the mode? Let me do a revision of the mode. Say for example, I have a set like 1, 2, 3, 3, 3, 5. So what will be the mode of this? Mode will be equal to 3, because 3 is multiple times. And even if I do a PDF or PMF like this, so 3 will have the, it will pull the mean towards it, and 3 will have the highest peak here, because the value around 3 is, means 3 has the maximum number and it will pull it around. The mean will be there or the peak will be around this, the PDF. So this is what it means. And the map estimate gives us this mode or the peak of the curve. Let me write it down. So it gives, this finds the, we will use this to find the peak or mode. I hope this peak and mode is clear. Okay, peak or mode of the posterior distribution. Okay, so let's begin. So this will be represented as theta map, as we did theta MLE in the last class. So this will be equal to, find the parameter theta, which is a maximum a posteriori estimate. This will be a point estimate for which, so which maximizes my posterior distribution, argmax theta, which will maximize my posterior distribution, theta given x, theta given x. This will be f or p depending upon whether it's continuous or discrete. So for example, if I'm using this is a continuous, then I'll use f, and if it is discrete, I'll use p. Okay, so this is a symbol. So this is my posterior distribution. So I have to find that theta which will maximize this, and this maximum would be around the peak of that posterior distribution wherever I get, like this. And this is there, or it can be this way, and this is here. So I have to find that peak. How will we do that? Let's see now. This is for continuous. Okay, so this is posterior, and this is for continuous case. Let me write it down so that the terms, the symbols are clear. And this will be equal to argmax of theta, probability theta given x, theta given x. This is your capital theta. Okay, this is a capital theta, this is small theta. This is capital X, this is small x. Okay, and this is for when theta is discrete. Theta continuous and where theta is discrete. So I'll have P. F is for the PDF of continuous random variable. So now let's understand. So these terms are clear. So let's see an example of Gaussian distribution. Last class we saw Bernoulli. Let's do a Gaussian, which will make it more clear and the mass would come out more here. Okay, so it will be more complicated with respect to maths, but you will understand the fundamentals better. So let's do it. For example, so we have a distribution, so we know that x is a Gaussian, and we want to estimate the parameters of that. So this is a Gaussian with n theta, and say we know the sigma square. Sigma square is equal to 1. The variance we know. Okay, and we want to estimate this. This is unknown. This is unknown parameter. So we know that the data is coming from a Gaussian, but we don't know the mean. This is the mean of the Gaussian. Okay, but we know the variance. Variance is 1. To make the problem simple, we will estimate only one parameter. So let's move on. So what's the, and let's assume that this is the underlying distribution of the data that we assume, and then that's what x1, x2, similarly xn or random variable Gaussian. Okay, so let's do case by case. So let's see, there's a first case as we did earlier. First case, we'll start with a uniform, get a distribution, get the parameters value, and then we will see when the distribution is not uniform or it is biased towards. We have some prior knowledge in the last case class we saw, right? We the theta was uniform initially, and in the other case the theta was equal to 2 theta, that it was biased towards 1. So theta was 0, 1. It was Bernoulli trial. So theta was more biased. We had the prior belief or prior that theta, in the first one theta was uniform, 0 and 1 are equally likely. Other case theta was 2 theta, means it is more biased towards 1. Similarly here also in the first case we'll see that theta is uniform. So we'll start with that. Okay, so here we'll assume that p of theta 1 is equal to p of theta 0 is equal to half. Both are equally likely. Okay, and let's model it as discrete. It was Bernoulli. We modeled the prior as a uniform continuous. Here it is Gaussian underlying distribution, and we are modeling the prior belief as a discrete. Okay, just to say show you that continuous and discrete can go hand in hand. It's not like the problem should be complete continuous or complete discrete. Okay, so this is the belief. So let me write draw the PMF for this. Say for example this is your PMF, and say this is 0 and this is 1, and say this is your half mark, this is half or 0.5. So you will have to, so this is not a earlier uniform. If it was uniform you will have a straight line, but PMF the probabilities are concentrated at points. So here you will have one concentration at 0, and here you will have one concentration at 1. Okay, so both are half of, this is our PMF. PMF for the discrete initial belief that both 0 and 1 are half of, equally likely. So this is a prior. This is a prior. The next, so for calculating posterior we need prior, then we need likelihood. So what will be the likelihood? Likelihood, we know it's a Gaussian. So what is the PDF of a Gaussian? Earlier it was Bernoulli. So this will be f of x given theta, x given theta is equal to, so PDF of Bernoulli would be, so it's the product of all. So it will be pi equal to 1 to n 1 by root 2 pi sigma e to the power minus xi minus mu whole square by 2 sigma square. Okay, this is our e to the power minus, this is our Gaussian. By now you should be used to this. Okay, Gaussian. So we know that sigma is equal to 1. Let's put this in this, f of x given theta, capital theta, x given theta is equal to is equal to pi I equal to 1 to n 1 by root 2 pi. The sigma is 1, so I'll let it be, and e to the power minus xi minus mu whole square. There will be nothing. There will be nothing in the denominator. No, it will be 2. There will be 2 sigma square. There will be 2. Okay. The sigma square is 1 here, and the sigma is 1 here, because that is initial. This is how what the distribution is we have started with. So what is the problem about? So we want to find the distribution. It's the Gaussian, we know that. So it's a Gaussian, and the mean is by either 0 or 1. Okay, so we know that. So there is the mean is either 0 or 1. It's a Gaussian with mean 0 or 1, and probability of having mean at 0 or 1 is equally likely. So how will this distribution be? So it will be something like this: one peak around 0, another peak around 1. Okay, so we have to find out what is the distribution like, whether it's this distribution or this distribution, either of these two. Okay, if theta is 0, so because only there are two possibilities, theta is 0 or half. That's how we have formulated the problem. So either my distribution is this or this, and you have to find out which one is it. Okay, so this is our Gaussian. So this is, I hope the problem is clear, and then let's proceed. Let's do the maths. So this is your, we had the prior, that probability of seeing theta is our mean, right? This is the theta mean mu at 0 or 1. Okay, likelihood, this is the likelihood. This is the Gaussian formula. The prior is 1. This is the likelihood. And now posterior, let's calculate the posterior. What will be the posterior based on the Bayes theorem? Posterior will again be it will be a distribution based on the prior. So whatever is the prior, my posterior will depend on that. So if it's a discrete, then my posterior will be a discrete. Okay, so what will be the posterior distribution? P of theta given x is equal to P of theta into, here it is f, it's a continuous because fx given theta, x given theta, by fx of x. This is the, let me write it down here also so that you remember. This is just a revision of what we have done. This is Bayesian. Posterior, this is my prior, this is likelihood. Okay, and this is the evidence, or this will be my marginal probability. Okay, all these terms, that is clear. So we have this is the initial belief. We know the distribution is Gaussian. Okay, that's the, we have to find the parameter theta. So given this theta, it is a Gaussian, and we have to find the parameter after seeing the data. What is my actual parameter now? We have to find that probability. That's two. We need to find, and we have to maximize the possibility of seeing that data. That's what the parametric model estimation means, right? So if I have to find such theta which will maximize the probability of seeing the data that we have seen, this x1, x2, xn, all this is the data we have seen. This is the data, right? Or the observation. So this will maximize the probability of seeing such a data. We have to find such parameters of the underlying model. Okay, so calculating this is the probability, this is the PDF of the underlying distribution, right? That's what we are trying to, but we don't have this information. This is the hardest part. So generally we try to get rid of this or try to solve it in another way. We don't know this. So this is a hard problem, getting this value. This is hard. Okay, so we'll see ways. Earlier also we have seen how to, we use beta distribution, and then we'll see how to get around this problem. So let's see. So we need to find, so this is a product, right? So we have seen this was a product. Let's write down, and then let's do it as a, let's take a log on both the sides. So we need to find this will be difficult. So for solving this, let's take a log on both sides. Okay, log on both sides because computing this will be very difficult without the parameters. We don't know anything. That's what we want to estimate. So this will be log of, okay, posterior log of p theta given x theta given x is equal to, so this is a product, the log of a into b by b, so this will be log a plus log b minus log c, the denominator. So log of sorry sorry log of p theta plus log of the likelihood, that is f of seeing x given theta, and then minus of log of f of x. Okay, and the task is find theta that maximizes the probability of observing the data. So we have to find the theta max. So this would be like, we need to find max, argmax theta. We have to find sorry p theta given x theta small x, which will maximize this probability. We have to maximize this probability, and log is a monotonic function. So log of, if x increases, log x increases. Okay, this is a monotonic function. So that's why I've taken log. It doesn't change, but it will make our math simple. So we time and again we'll be taking log in everywhere, because it will make our math simple. It will convert the product into sum. So let's find out. So what we do? So now generally when we try to find the max of something, what did we do earlier? We'll take the first derivative and equate it to 0. That will be our point of optima, maxima or minima. But here taking the derivative of this and equating it to 0 will be very difficult. Okay, because and also we don't need to do that. We can have a simpler way to solve this. Okay, because this part is the difficult part, because we don't have, this has nothing to do with theta also, first of all, and again differentiating it with respect to theta, this will again go to 0. But we just need to find, we have two values, so why to differentiate and find all the possible values where it will be. So here our prior says that my theta or the mean is either 0 or 1, so there are only two possibilities. So we can directly calculate the two possibilities and compare the values instead of differentiating and going that harder way. So that will make our task easier in this case. So what we'll do is, we'll check for only these two values, theta at 1 and theta at 0, because that's what we have to find, that theta has only, this is the mu will have only these two values, mu is equal to 0 or mu is equal to 1. These are the two possible. That is the prior belief we had. These are the only two values. This is the distribution. Okay, so what we'll do also, when we want to compare with two values, also this fx of x doesn't have any theta, and computing this is difficult, so we can get rid of this when we compare two values, right? And this value is common in both of them. So when we add or subtract the same thing on two terms, it doesn't make sense. It doesn't add any value, so we can ignore this. Say for example, if I'm comparing two values, say 5 is greater than 3, right? If I subtract 2 from here and 2 from here, it will be the same thing. 3 is greater than 1, the equality or inequality remains the same, right? That's what we want to do. So this is your extra part. So I want to get rid of this. I don't want to calculate this. Okay, so that's why we have done. So let's move on. How do we do? So we have two values. We want to calculate at 2 points. Log of probability of theta given x is equal to log of p theta of theta plus log of f x given theta minus log of fx of x. Okay, so we will put theta equal to 0 and we'll evaluate it theta equal to 1. Okay, so let's evaluate. So log of probability of theta given x, and let's put 0. So first we'll put 0 given x is equal to log of p theta p theta 0 plus log of what is the distribution. So with the distribution we had, right, for the Gaussian f of x, this is the distribution, log of this term plus log of 1 by root 2 pi, okay, e to the power minus x minus mu I whole square by 2, and minus log of fx of x. This is the similarly. So here instead of mu I, this will be 0. I'll put all the values wherever theta is 0. Mu was 0, and then we'll have log of p of theta given x, 1 given x, seeing 1 given x is log of probability of 1 plus log of 1 by root 2 pi e to the power minus x minus 1 whole square by 2 minus log of fx of x. From now on, both the sides are having this. I won't consider this value. Sorry, I won't consider this value. So this is common in both the sides. I want to compare. Now either of these two terms can be greater, this or this. Okay. So let's assume that theta equal to 1, that is the greater term. Okay. So for this, this value to be greater than this value, okay, what should be the case? Okay, if this is greater than this, so let's put down the value. So what should be the case? So here I'll put it. So this is theta equal to half. So this value we know. This is theta 0. Probability of theta is 0. Is that's a prior belief. Both are same. P theta 1 and P theta 0. Sorry. Both are same. That are half. This is equal to half. This is equal to half. We know that. And we'll expand the second term also. So this is same for both the cases. And now for this, for one case, for theta equal to 1, log of p theta given x, 1 given x should be greater than, if I want that, this is that one side is greater, assuming what will be the calculation be like, log of p theta given x, 0 given x. Yes, sorry. Okay, let's continue. So what will be this value? This will be equal to this second term. So here, if you see, this is common. I'll cancel this out. Okay, this is common in both. This is also common. So only thing that compares is this value. Log of the Gaussian part. We'll compare this, and I'm assuming that this is greater than this. This value is greater than this value. Okay. So for this to be, for theta to be 1, sorry, not log. So there are only two possible values. So for theta to be 1, if this probability is greater, means log of some probability is greater, then this theta is equal to 1. I have to calculate either or this value. So whichever value calculates greater, that will make that I can choose 1 as the value. And if this becomes greater, then I can choose 0 is the probability. So I have to find out which one comes there. Okay, so let's see. So what is this coming to? This will come by. So this will be expanded. So there will be some maths, follow along. Okay, if not, just do it on your own later. So this will be again, this was a product, right? This was pi I equal to 1 to n. This was the product n times. Okay, so this will become to the power n will be there. So I'll just make it simple. Okay, so this will be, so what will be this one? So this, let me just expand this Gaussian term, log of 1 by root 2 pi minus x minus mu y whole square by 2. Okay, so this whole term, so this will be there, product of this plus, okay, this will be coming n times, this will become power n. Okay, and when I take log of this, this n will come outside. I'm just giving you one hint, and then rest of things you can just figure out. So this will come multiplied n times, so this will become n times outside. And when I take log that power n, okay, this thing multiplied n times will become, it will be, its power will become n, right? And I take log of this after doing this pi. Okay, if I take, this will become n log, so n will come in front, this will become n log 1 by root 2 pi, the first term, and then log and exponential will cancel each other, right? So it will become, and this whole product will become a summation, the second part. Okay, the second part. So this, it is a product plus this exponential will cancel out the log, and plus this product will become summation. Okay, I equal to 1 to n xi minus mu whole square by 2. Okay, I hope this is clear. And because of this minus will come here. This minus is direct. This will cancel out only e. This minus will come as it is. So this will become e. This will become minus here. I hope this is clear. How I have taken log of this. Right. So this product, this has power n. So this n came here, and this product of this made its summation, and e was cancelled out by log, and the rest of the term came as it is. I hope the math is clear. Okay, so let's see again. So if you see this n log root 2 pi, okay, n log 1 by root 2 pi, this is common, this will be common for both, because this term is common here, this is here and here also. Okay, I equal to 1 to n just for this, and here also I'll write mu I. So this was 0, but I'll, okay, 0, that doesn't change anything. Okay, so this is here. So this term, what I'm saying, is common in both, so I can get rid of this also. Okay, so let me write it down again so that it's clear for you, all the terms together. Log of probability of theta given x, of saying first, okay, 0 given x, is equal to log of p theta, that was half, plus log of 1 by root 2 pi minus log of, okay, minus this log, and this will cancel out, so this will, log will go off. So that second term from here, sigma I equal to 1 to n xi minus 0 whole square by 2, and fx we have already got rid of, and then log of p theta given x, 1 for case 1, this will be again, both cases are half, plus log of 1 by root 2 pi n times, okay, minus, I'm just missing it because both are same, so it doesn't matter, not x, xi, this will be there by 2. Okay, both are same, fx already got rid of, and this is also same, so I'll get rid of this. So only thing that remains is this and this term. So for this to be greater, so for theta to be 1, for theta equal to 1, if I say that theta is equal to 1, so this probability should be greater than the above probability, means this term should be greater than this term. So this term should be greater than this term. So finally this will come as, for theta to be 1, minus sigma I equal to 1 to n xi minus 1 whole square by 2 should be greater than minus sigma I equal to 1 to n xi minus 0 whole square by 2. I hope this is clear. For theta to be greater than 1. For theta equal to 1, for theta to be 1, not 0, this term should be greater than this term. Only then this will hold. Okay, let's continue. So this implies, what will be the case? Sorry. So I'll bring this term also here. Okay, this will become sigma I equal to 1 to n xi, let it be xi only, xi square by 2 minus sigma I equal to 1 to n xi minus whole square by 2 is greater than 0. Okay, so what will be this equal to? So I'll just keep sigma I equal to 1. Okay, and this 2 half will be common, and this will be coming sigma n times, so 1 by 2n will be common in both. Okay, so this summation n times will become n in both, so I'll take this 2n common and bring it out. And let's expand it. Xi square, and what will be this? Minus xi square minus 2xi plus 1 is greater than 0. So this implies 1 by 2n. So this will be, this and this term will cancel out because that's negative, and then remaining minus minus plus, this will become 2xi minus 1 is greater than equal to 0. Okay, so this is equal to this implies that sigma again. Okay, so let's do the maths. Sigma, okay, I equal to 1 to n. This is for all. I equal to 1 to n. This is 1 by 2 n times. Okay, and this will be 2xi. This will be 2xi times. So let's do a separate. So this will be sigma 2xi minus sigma I equal to 1 to n. This will become minus n. Okay, I have done the summation. So the sigma remains here. Sorry, the sigma remains here. The 2xi, and this will be greater than or equal to 0, and this implies what will be the value? So this will be here 1 by 2n and this n, so this will go out. Okay, so let me, this bracket will hold. So sigma I equal to 1 to n 2xi, this will be 1 by 2n minus n by 2n is greater than 0. This n and n cancels out. This implies, so I have just opened the bracket. Okay, so this will be sigma 1 by 2n 2xi is greater than 1 by 2. This 2 and 2 will cancel out. This is I equal to 1 to 1. This implies 1 by n sigma I equal to 1 to 1 xi is greater than half. This was n and n by 2 has come this side, right? So this is our final conclusion. So what is this value? 1 by n sigma I equal to 1 to n. We have seen this in the past, right? This is your nothing but, this is the mean. Sum of all values divided by the number of terms. Sum of all the terms divided by the number of terms. This is the mean. Okay. So how can we write? So our theta map, what will be my theta map? Should be greater than half. What did we assume? That for theta equal to 1, what should be the condition? For theta to be 1, my theta map should be the average, the mean should be greater than half. When, so I said that mu I is either 0 or either 1. So if summation of all the values, if it is greater than 0, means it is 1, and if it is equal to or less than 0, okay, then this will be 0. So what will be my theta map equal to? So this whole, that assuming that this is greater, finally we came to that the mean should be greater than half. And if we write it mathematically in a condensed format, how do we write it? This will be equal to 1 if 1 by n sigma I equal to 1 to n xi is greater than half and 0 otherwise. Means when the mean is equal to half also, or anything less than or equal to all the remaining part, right? Then this will shift to 0, and if the mean is just greater than half, then it will go to 1, and that is when our theta is the theta is uniform. Assumption is there is equal probability of it being 0 or 1. Okay, so this is the whole maths. I hope this is clear. So we got a point estimate when it will be 0 or 1, right? So this is clear. So this is your case 1, when the prior was uniform. So I'll write it here. This is uniform. That is equally likely to be 0 or 1. And what was the second case? We did in the last class also. Second case was that it is biased more towards 1. Or let's see another example. We have seen this already. So I'll just change the example. So my case 2 would be that my prior information. So my prior information that I have is probability of seeing theta 1 is less now, 1 by 4, and probability of seeing theta equal to 0 is more now, 3 by 4. I did opposite now. Okay, so in this case what did we see? That when priorities are equal, 0 and 1, and there will be a 0.5 in the middle. So if my value is just greater than 0.5, it will become 1, and if it is less than 0.5, then this will become 0. So this region, if my theta falls here, whatever the calculation, the sum of these things come. Okay, so if it falls here, theta will become 0, and here if it falls here, theta will become 1, where it was uniform. And let's see, now we have a more prior information that theta is more biased towards, it is having more likelihood or more tendency to be towards 0. It is 3 by 4 and only 1 by 4 towards 1. So let's see how does this impact. So this was with the uniform prior. Now what will be my map estimate based on this? So I'll take all this calculation till log as it is, and then I'll compute from there. So let me copy that where it was. These two terms. I'll just make modifications here, and I'll take it from there. And this time the calculation I'll do it fast so that you understand. So now you have got the hang of it. Now you should be able to follow along pretty fast. This time these values are different. So let me rub things off. So here this is different. These terms will remain as it is, but this time this is not half. Here this is 0 is 3 by 4 and 1 is 1 by 4. Rest of things remain same. Okay, that's the only difference. Earlier it was half, equal. Now this time the prior information is this. So how will we calculate? Again, we want to check that if theta is, for theta to be 1, I want, if theta is 1 means this term should be greater than this term. So we'll calculate it that way. So my bottom term, that is log of 1 by 4 minus sigma I equal to 1 to n xi minus 1 whole square by 2 is greater than the bottom term, upper term, log 3 by 4 minus sigma equal to 1 to n xi whole square by 2. This should be greater, only then theta will be equal to 1, because the probability of seeing 1 is greater, and the log of that will also be greater. So that's what I'm equating to. Okay, so for theta to be 1, this should be greater, and this, I have got this equation now. So let's solve it quickly. So this will be equal to so this will be log 1 by 4. So I'm just checking. So I'll bring this, all these terms one side. So this will be log 1 minus log 4 minus sigma I equal to 1 xi minus 1 whole square by 2 minus log 3. I'm bringing it from that side. Minus minus plus log 4, and this minus will become plus sigma I equal to 1 to n xi whole square by 2, and this whole thing should be greater than 0. Only then my theta will be 1, because the probability of that will be 1. Now let's cancel out some terms. Log 4 is there, log 4 is here, that will go. So this will become log 1 minus log 3. Okay. So this is there. Sigma positive I'll bring here. I equal to 1 to 1. And I'll bring all these terms together. Okay. Half I'll take it common. Xi square minus xi square plus 2xi minus 1 is greater than, I'll take back this side, log 3 minus log 1. Log 1 is 0. Why have I not? Log 1 is 0. Okay. So we'll get rid of that. So this is greater than log 3. And we have seen this calculation earlier. This calculation. This is the same calculation, right? This is the calculation that we are doing. What did this come out to be? Xi square minus this thing. This is the same calculation that we are doing here. Let me write it down in the same format so that it's clear for you. Half of xi square minus sigma I equal to 1 to 1, or within the same, and we brought this 1 by 2 and outside, right? Minus xi minus 1 whole square. This is the same thing. So this one, what did it come out to be? This is greater than half. Finally, this gave me that this mean should be greater than half. Finally, we calculated and we found that this should be greater than half. Okay, so we'll just put it as it is to avoid the confusion. So this will give me sigma 1 by n 1 by n I equal to 1 by n xi is greater than half, and this is log 3, so this will be plus log 3 will also be, because this is already there. So I'll just substitute this value, and now this is greater than half, and plus I have, earlier it was 0, and now I have one more log 3 term already, because of, but earlier it was log half minus log half, now this is log 3 by 4 minus log 1 by 4, and rest of the terms come as it is. Okay, right? So when my prior is biased towards 0, now what will be my theta map? My theta map will be equal to 1 if my mean, this is my mean, right? I equal to 1 to n xi is greater than half plus log 3, 0 otherwise. Oh, sorry, log 3 by, oh dear, so if it divide it, right, so log 3 by n term will come here. Okay, so after solving this n term will divide here. Earlier it was 0, so that's why it went off. Now this log n will come here. Okay, so just do the maths, you will get it. It's simple, just equating. Okay, so thus log 3 by n term will come. Just solve it step by step, and you will reach here. You will divide at one step, you will divide by 1 by n on both sides, and then you will get it. This n common that I came up, that I missed out from there. Earlier it was 0, so no problem, but now it is, there is a term, so that's why it will divide this side also, and that's why you will have this. I hope that is clear. So this is our theta map for a biased prior. Okay, and how will this look like on the number line? Say for example, if I have the number line, earlier we said that this is 0, this is 1, and then this is here half. Earlier the likelihood was that if this is this side, but now we have got one more term, that is log 3 by n half plus. So now this will be 0 till here, and then only if it is greater than this will be in this. So here this will be 1, and here this will be 0. So now if you see, because the prior is more biased towards 0, so my probability, it is extended beyond half log till log 3 by n. Until this point it will be 0, and only after that. So that's the impact of the prior. And as I said, right, as n grows high, the impact of the prior will be gone, and this will again tend to half only, right? So this becomes very, very large. To 3 by n will become very small, okay, and that will tend towards half. Then that will become equal to no prior information. Okay, I hope these two cases are clear. So what is the conclusion for a non-uniform prior? So earlier the uniform prior is there, right? So for a non-uniform prior, my estimate will be pulled towards the prior if it is non-uniform. This non-uniform is this. This is non-uniform. So my estimate is pulled towards the prior, and that's what we are seeing, that it is pulled more towards 0 because it is valid only in the range 0 to 1, and it is pulled more towards 0 than 1. And that extra term is log 3 by n, because that is coming from this probability 3 by 4 and 1 by 4. Okay. So this map is good for, so here map is good for what is that? I'll give you some notes. So this map is good for classification problem. You want 1 point estimate. Okay. Map is good for classification problems. Classification means yes, no kind of. Yes, no, right, wrong, 0, 1, that kind of. So that's where we can get a binary output, one or the other. So in that case, this will give me whether what is its probability of being 0 or 1, yes or no, right or wrong. Then map estimate is good. Okay.